Recording now. Okay, hopefully everyone can see the screen. Hello? Uh-oh. That's not good. Oh no, it happened again. Yikes. Hello, I'm back. Sorry about that. Everyone still here? Can everybody hear me? Yeah, okay, sorry, my computer froze for a minute. Sorry about that. Okay, great. Okay. All right, okay, great. Give me one moment again. I'm gonna just set the screen up again. Yep, we're gonna start chapter 2.1. Okay. Oh, we had a question about the next quiz. Well, let's see. We're going to do hopefully section 2.1 today. Oh, next week, I believe Monday, we don't have class, if I'm correct. So we meet again next week on Wednesday. Let's make our next quiz the week after that. Okay, so not next week, but the week after that. Your screen isn't sharing. Oh, yes. No, give me one moment here. I'm going to share the screen. I'm not sharing at the moment. Okay, I think this Monday is Columbus Day, if I'm correct. I think college is closed. All right, I'll double check that to make sure. But right. Okay, all right. So next week I'll confirm the date for the quiz. Okay. Are the exams cumulative? No, the exams will not be cumulative. Okay. All right. So just give me one moment. Let me get my my other screen up here for a moment, and then I will share it. Oh, cumulative meaning the exams will not cover old material. Every exam will only cover the new material. Okay. All right, we're up and running. Let's begin. Is it technically the information technically cumulative? Yeah, well, yes, in a certain sense, there are certain things you'll need to remember from the previous chapters that will influence what we're going to do. Okay. All right. Okay. Okay. All right, so we're going to now begin chapter 2, section 2.1. All right, so chapter 2 is going to deal with a bunch of different topics. The foundation of what we're going to discuss in chapter 2 is our sets. Okay, so we're going to start by discussing sets and set operations. And from there, we'll use sets to define what functions are. We'll use sets to define sequences, and then we'll also discuss sums and matrices. Okay. So we're going to discuss in chapter 2 sets, functions, sequences, sums, and matrices. Okay, many of you may have seen several of these topics previously. For some of you, some of this stuff might be new. Okay. All right, so we start by defining what a set is. All right, so it's chapter 2.1, sets. Okay, so the definition of a set is a very broad definition. Okay, so let's start with that definition. Definition. A set is an unordered collection of objects. Called elements or members of the set. Okay. A set is said to contain its elements. Okay. And there is notation that we use to indicate that something is an element of a set. So we write capital letters will be used to represent sets. Okay, so this means this little letter A is an element. That E-looking thing means element. A is an element of the set A. Okay, so use this to denote that this lowercase letter A is an element of the set A. Right? Okay, so the capital letter represents the set. Okay, if I want to say something is not an element of a set, right? It's not in the collection. All right, I just put a slash through my symbol here. Okay, so this means A is not an element of A. Okay. All right. So we use sets in math, and not just in math, and on many different disciplines all the time, right? In math, we use sets all the time. Like, for example, if I want to talk about a certain collection of numbers, I'll call that a set. So let's say I'm doing a certain problem, and I only want to talk about whole numbers or integers. So I talk about the set of integers. That's the number. Those are the numbers I'm dealing with. Or if I want to only deal with the numbers from 1 to 10, let's say the integers from 1 to 10, that could be a set. Okay, that would be a set of numbers. Okay, that's a collection of numbers that I'm dealing with that are in my group. Okay, it doesn't have to just be that. I could have a set of anything. It doesn't have to be numbers. So if I'm let's say I'm a school. A class could be a set where the students in the class are the elements of my set. Or if I have a computer lab, the elements of my set could be the computers in the lab. I want to discuss the computers in the lab. Those are the objects in my set. okay? Or if I'm an airline or I'm an airport, okay? The cities that my planes fly to could be a set, right? I have a set of the cities that I have flights to and from, okay? And so on and so forth. So a set could be a collection of any objects, okay? And it's an unordered collection. So order doesn't matter. There's no first, second, third, fourth, okay? You're either in the set or you're not in the set, okay? All right, so what could be examples of sets? I said a few. Let's write out a few examples. Okay, so the following are examples of sets. Okay, so number one. Now, every time I write a set, usually I will enclose it in braces. So this is an opening brace. And then I just list out the elements in my set, and I'll separate them with commas, okay? So let's say I want to discuss the set of numbers. What did I say before? The set of numbers from 1 to 10, the whole numbers. So I can write that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? So this here is a set, all right? It's a set of 10 numbers, the integers, the whole numbers from 1 to 10, okay? And if I want to give my set a name, I'll usually call it by a capital letter. So let's say I want to call this set here S. All right, S is equal to this. This is the set S. Okay. I could have another set. I could have a set where my elements are, let's say, letters here. So A, B, C, D. Okay. I could have another set that's called my next set B, where my set here is cities. So I could have New York City, Los Angeles, Chicago, okay, and so on and so forth. Okay. Now, the way I've been listing the sets so far is by writing them in braces and just listing all the elements. Okay, that's one way of writing a set. It's called the roster method. Okay. So there are several ways to describe a set. Okay. One way is to list all of its members. Okay, this is called the roster method. Okay. Right, so whenever we use the roster method, using the roster method, we enclose the set in braces. Okay. Another example of a set. Now, sometimes my set is very, very large. Let's say I want to deal with the integers, the whole numbers from 1 to 100, and I want to list out using the roster method. So instead of listing them all out, a lot of times what we do is you list the first couple of elements so that you can see what the pattern is, if there is a pattern. And then I write 3 dots, which are these 3 dots are called an ellipsis, to indicate that the pattern continues. And then at the end, I write the last one. All right, so these are the numbers 1, 2, 3, and these 3 dots, so to speak, mean like et cetera, until the number 100. Okay, so that would be the integers from 1 to 100. Yes, yes. So all the examples I've given so far are the ways of describing a set using the roster method. Okay. Okay. Another way of describing a set is instead of listing out all the elements in the set, instead you can describe or give a description of what elements are in the set. Okay, and that's called set builder notation. Okay, so another way to describe a set is by using set builder notation. Okay. So with set builder notation, we characterize all elements in the set by stating the property or properties they must have to be members. Okay, so for example, another way to list a set. Let's say I have a set S. Okay, and this set is going to be a set of all positive integers less than or equal to 10. So that would be the numbers 1 through 10, which we did before. Okay, so one way I could do it would be to write S is equal to all X, and this is how I do set builder notation. All right, S is equal to all elements X. Then I write a line here. This line means such that. So this is all X such that, and then I describe what X has to be in the set. So S is equal to all elements X such that X is an odd, is a positive integer less than or equal to 10. So I'll just write it this way, less than or equal to 10. Okay. All right, so this is the set 1 through 10 that we wrote before. I just, instead of writing it using the roster method, I've now written using its set builder notation. Okay, so here is set builder notation, and I'm going to write it again using roster notation. Okay. All right. Okay, so set builder, roster. Okay. So again, in the roster method, I just list out all the elements. In set builder, I write it this way, where I describe the elements in the set. And again, it's in braces. Okay, and so this is the same set, just written out in 2 different ways. Okay, so again, this is read as all X such that X is a positive integer less than or equal to 10. Okay, now if I have a very, very large set, a lot of times we don't want to list all the members out. So instead, many times it's more convenient to use set builder notation, where I just give you the description of what you have to be in the set. Okay. Okay. All right. Any questions so far? Okay, so there are several types of sets that are very important, and we've actually discussed a few of them, I believe, previously. Okay, so I'm just going to give you those sets. These sets also have special symbols that represent those sets. The ... is usually used in the roster method. That is correct. It might also sometimes be used in the set builder notation, but it's usually used in the roster method. Okay, it's used a lot in mathematics. ... When you have a list and you want that, the ... implies that the list continues, like the pattern continues. All right. Okay, so I'm now going to give you some important sets. All right. All right, some important sets. Okay, and again, some of these we've seen before. So the first set I'm going to give you is a set known as the set of natural numbers. Okay, so the set of natural numbers. Okay, it's denoted with a bold N. But whenever we write it, we can't write in bold, so usually I'll just put a double line there by the N. Okay, so this is an N. This N here represents the set of natural numbers. The set of natural numbers are all of the non-negative whole numbers. So it's all the whole numbers starting from 0 and going up. So 0, 1, 2, 3, etc., etc. Okay, and that goes on forever. So I have 3 dots implying that the list continues. Okay, so this is the set of all non-negative integers. It's the set of non-negative integers. Ooh, sorry. Okay, now the set of natural numbers, there's actually, in different texts, there's a little bit of a disagreement as to what should and should not be included in this set. Okay, in some textbooks, 0 is included, and in some textbooks, 0 is not included. In our textbook, 0 is included, so I will include 0 in the set of natural numbers for our purposes. 0 is a whole number, yes. 0 is a whole number, yes. 0 is an integer. Okay, it's non-negative, right? 0 is neither negative nor positive. Okay. Okay. So anytime I say non-negative, I mean 0 and positive numbers. Okay. If I say non-positive, I mean 0 and the negative numbers. Okay. All right. The next set is the set of integers, which is a set we discussed before. Yes, that is correct. Some people do not consider 0 to be part of the natural numbers, and some do. So I'm just going to follow the textbook for our purposes, okay? And all right, the set of integers. The set of integers is represented by a letter Z, either in bold or with a double line like this, okay? The set of integers are all of the whole numbers, including the positive and the negative whole numbers and 0. All right, so it includes positive and negative, well, it includes 0, positive and negative 1, positive and negative 2, positive and negative 3, etc., etc. Okay. If I want to refer to only the positive integers, I write it as Z plus. So Z plus, anytime I put a plus, it means only the positive one. Z plus is the positive integers. Okay, so that would be 1, 2, 3, 4, 5. Okay, so etc., etc. 1, 2, 3. Okay, so the natural numbers, it's convenient to have the natural numbers include 0. So this way I have a symbol for the natural numbers, and I have Z plus to represent the positive integers. This way I can distinguish between the two, right? Depending on whether or not I want 0 to be in the set or not. Okay. And Z minus would be the set of negative integers. Okay, so Z minus would be negative 1, negative 2, negative 3, etc., etc. Okay. The next set would be the set of rational numbers. Okay. So the set of rational numbers are a type of real number. All right. The symbol for it is Q. It's a bold Q. Again, since I can't do bold, I usually write it with a line going through it. Okay. Does anyone know what the definition of a rational number is? I hope you guys do know the definition. We've discussed it a few times, right? Yeah. Exactly.
P over Q as long as they're integers?
Yep. One more thing. You're missing one part.
Q is not 0.
Yeah.
Q is not 0.
Exactly. Perfect. Good. Okay. Okay. So I'm going to write it here using. So P and Q, they do not. So for the definition of rational numbers, is a good point. In the definition of a rational number, P and Q do not have to have P over Q does not have to be in simplest form, right? That was a separate principle that we used when we did the proof that the square root of 2 is irrational. Okay, so that was a separate idea. It's not actually part of the definition of a rational number. Okay. Okay, so let's write this down using set builder notation. So Q is equal to P over Q, such that P is an integer, so I'll write it this way, right? This means P is an integer. P is an element of the set of integers. Q is an integer. Q is an element of the set of integers. And Q is not equal to 0. Okay, so 3 conditions. P and Q are integers, Q is not 0. Okay. All right. Next is the set of real numbers. Okay, that's represented with an R. R is the set of real numbers. So what are real numbers? The set of real numbers are all the rational numbers and all the irrational numbers. Okay, so that includes everything that is a whole number, everything that's a fraction, everything that can be written as a fraction, right, as an integer over an integer. Okay, so for this, all right, R is the set of real numbers, and R includes all the rational and irrational numbers. Okay, I'm just going to write it this way. Okay. And again, if I wanted to refer to the positive ones, I would write R plus. If I wanted to refer to the negative ones, I would write R minus. Okay. There is one more set that's commonly used. We're not going to really use it in this class, but you've probably seen it before, or you might see it again. So let's discuss that set, the set of complex numbers. Okay, so the set of complex numbers is represented by a C. All right, it's a set of numbers that include imaginary numbers, right? Imaginary numbers are numbers that include the square root of -1. All right, so this set, and again, I'll write this out using set builder notation. It's the set of all numbers of the form a plus bi, such that a is a real number and b is a real number, and I is equal to the square root of -1. Okay. Okay. All right. So those are important sets. These are all, by the way, these are all also infinite sets. They have an infinite number of elements in them, right? They're not finite. Okay. We'll use these symbols a lot throughout this section. Okay. By the way, you can also have a set whose elements are sets, right? The elements of a set can really be anything, right? So the elements of a set can be anything. Well, to be honest, not anything. If you let your set, the elements be anything, then you run into Russell's paradox, which maybe I'll give you a problem with that for homework. But basically anything. The elements of a set can be anything, including other sets. Okay. So for example, I could have some set S whose elements are include, let's say, the number 1, and also include a set. Let's say a set including that has the numbers 1, 2. Okay. So here is a set. Okay. That has how many elements? How many elements are in set S here? How many distinct elements? Yep, there are 2 elements in here. Okay. What are the 2 elements? 1 is an element of the set S. Okay, the number 1. And also this set, including the numbers 1 and 2, that set is also an element of the set S. Okay, so S has 2 elements. The number 1 and the set 1, comma 2. Okay. So is the number 2 an element of S? Let me ask you that. Is the number 2 an element of the set S? What do you guys think? Right. Right. 2 is not an element of the set S. Okay. So the number 2, no. 2 is not an element of the set S. Okay. Why not? Because the number 2 does not appear as a number by itself in this set. Okay. I have only the number 1 and a set that includes the numbers 1 and 2. Okay. Okay, so the number 2 is not an element of the set, but it has, yeah, it's a subset. Well, not exactly. Not exactly. Wait. It's not a subset either. Okay. It's an element of a subset of the set, but yeah. Okay. All right, we'll get to subsets soon though. Okay. If you want, usually an example that I give to sort of think of it, just in case it's a little confusing. Let's say that you're on your computer and you open up your documents or something like that. You open up your documents, okay? You open up a folder. So let's say S is a folder, okay? I click on S, the folder S. What do I see? I see 2 objects. I see a file. That file is the number 1. And I see another folder. So we're thinking of sets as folders in this example, okay? So I have a file, the number 1, and I have a folder. And inside that folder is the number 1 and 2. So when I click on S, what do I see? I see a number 1, and I see a folder. But I don't see the number 2. Okay? Okay. All right. Let's now talk about when we consider 2 sets to be equal to each other. When are 2 sets considered the same set? Okay. So definition. And this is definition for equality of sets. 2 sets are equal if and only if they have the same elements. Okay, so therefore, we can write this out using logic. All right, I'm going to write that out now. So therefore, if A and B are sets, okay, so A represents a set and B represents a set, then A and B are equal if and only if, I'll just write IFF, that's short for if and only if, for every element X, okay, X is an element of A, if and only if X is an element of B, okay? That's what equality means. It means that if an element is in one set, it's also in the other set, okay, and vice versa, okay? So they're equal only if they have exactly the same elements. Any element that I can find in one, I can also find in the other, and vice versa. Okay. We write, if they're equal, we write A equals B, if A equals B. Okay, right, we use the usual notation for equality. Okay, so somebody's asking, what is the domain of X? Well, here there really kind of isn't a domain. It just sort of means, well, the domain is the elements. So whatever elements of the set are, though that's sort of my domain. Okay, so all we're sort of saying is that whatever is in one set is in the other set and vice versa. Okay, so we think of the domain as the set of elements. Okay. All right, somebody asked me to repeat something, but I'm not sure what you're referring to.
regardless of its order, right? It's the lists that are ordered. Sets aren't ordered, right?
Sets are not ordered; they're unordered. So order does not matter. Okay. So let me demonstrate this. Let me demonstrate this with an example. Okay. So since you asked me about order, okay, let's say I have a set A that has in it the elements A, B, and C. Okay. And a set B that has in it the elements C, A, and B. Okay. These two sets are the same set because everything that's in A is in B, and everything that is in B is also in A. Okay. Right. A, B, and C are all elements of A, and A, B, and C are all elements of B. There's nothing in A that's not in B. There's nothing in B that's not in A.
What if there's a repetition of the same element? Does that still equal?
Yes, excellent. That's where I was going next. Yes, even if an element is repeated, it doesn't matter. They're still equal because I can still find that element in the other set. That was going to be my next example. All right, so let's do that. I'll write that one after this. Okay, so order doesn't matter, right? Order doesn't matter with sets. These are the same. So A equals B. Okay. Next example, let's discuss repetition. So let's say I have a set A that has the numbers, let's say 1, 2, and 3. And let's say I have a set B that's got the numbers 1, 1, 1, 2, 3. Okay. Again, these sets are considered equal. Why? Because every element that's in B I can find in A. Okay. So order doesn't really matter. So the element 1 is in B, right? I see it. It doesn't matter that I see it 3 times. What matters is that it's in the set. Okay. So the number 1 is in B. The number 1 is in A. Okay. The number 2 is in B. Right. The number 2 is in A. The number 3 is in B. 3 is in A. Okay. So order doesn't matter. Repetition does not matter. Okay. It does not affect equality. Well, so somebody made a comment here. The sets are of different size now after repetition, right? Well, that depends on how we define the size of a set, which we'll get to soon, okay? As we'll see soon, when we define the size of a set, we do not count repetition when defining the size of a set, okay? So these two sets would actually be considered to have the same size. Okay, when we're looking at the size, we look at the distinct elements. We don't look at repetitions, okay? So they are considered the same set. Oh, can I scroll up? Let me do that. Here, how's that? Okay. Okay. All right. So what kind of set? What would be an example of two sets that are not equal? All right. So let's. I think everybody would figure that out pretty quickly. But let's do an example of that together. Okay. So again, let's say I have a set A that has the numbers 1, 2, and 3. B is a set that has the numbers 1, 2, 3, and 4. Okay. These two sets are not equal. Why? A is not equal to B. Why? Because I have an element in B that's not an A, right? 4 is in B, but, excuse me, 4 is in B, but 4 is not in A. Okay, so if I can find even one element that's in one set but not in the other, they are not equal. All right. One more example, perhaps. Let's say I have the set A equals that. This is the set from before. It has 1 and 1 comma 2, and I have this set here. Okay. Are these two sets equal? What do you guys say? Equal or not equal?
No, unequal.
Yeah, that's right. Yep, they're not equal. Okay. A does not equal B. Why not? Well, first of all, there's an element in A that's not in B. This set here, the set 1 comma 2, that's an element in A, but it's not an element in B. So it's in A but not in B. And also there's an element in B that's not in A, right? 2 is in B, but 2 is not in A. Okay, so there's two reasons why these sets are not equal. Okay. All right. As we see when we're going to discuss subsets in a moment, we'll see soon that B would actually be a subset of A, even though it's not equal to A. All right. Okay. Any questions so far? Would those be equal? Yes. So somebody wrote here in the chat, would let me write this out. Would these two sets be equal? Let me write them out. And the answer is yes, they would be equal. But let me write them out here. Would this set and this set be equal? Then the answer is yes, they are equal. Okay, because the order does not matter. So if I put 1, 2 or 2, 1, that's the same thing. Okay. 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 Or again, so order doesn't matter. So these two sets that I wrote out would be the same. It doesn't matter if I do 1, 2 or 2, 1. The order doesn't affect anything. Okay. Okay. 2 is not of A. Oh, you're referring to the example from before? I'm sorry, I didn't follow your question. If you're referring to the previous example, then yeah, again, 2 is an element in B, but it's not an element in A. Okay. Also, this set 1, 2 is an element of A, but it's not an element of B. Right? So the two sets there are not equal. Okay. All right. Let me give you a couple more definitions now. Okay. Right, so we start with the definition for the empty set. Okay, in set theory and sets, we have something called the empty set. That's the set that has no elements inside of it. It's got nothing inside of it. Okay. So the empty set, which is also known as the null set, is the set that contains no elements. Okay, it's got nothing inside of it. It's a special set. It's a very special set in set theory. Okay. All right. So it's denoted as follows with braces with nothing in them. Okay. This is a set that has no elements. Right. Like if you go back to our example of a computer folder, it's like you click on a folder and there's nothing in there. Okay. We also denote it with a special symbol, a 0 with a line going through it like this. Okay, so there's two different ways to denote the empty set. Either way is used. Okay. There's also a term for a set that has only one element in it, and that's called a singleton set. Okay, so a set with one element is called a singleton set. Okay. All right. Let's now move on to describe subsets. Okay, so we've described sets and what it means to be an element of a set. We're now going to talk about subsets of sets. Okay, so definition. So the set A is a subset of B if and only if, IFF, if and only if, every element of A is also an element of B. We use the notation So we use this notation here to indicate that A is a subset of B. Okay. So again, what does it mean for A to be a subset of B? Just explaining this again. So A is a subset of B. Well, if A is a subset, that means it's a set. And it's a subset of B if every element that is found in A is also found in B. Okay. So if you want, you can think of it like as follows. Think of B as being some very large set. Okay. And then I take some of the elements that are inside of B and I create a new set with those elements, with just those elements. So that new set would be a subset of B. Okay. If you want, you could even think of it as a Venn diagram. You guys are sort of familiar with Venn diagrams? We can use Venn diagrams to sort of draw a picture of what a set looks like. Okay. So if you want, you could think of this circle as representing the set B, and a subset A would be a circle inside of that. Okay, so here are some elements in B. These dots represent elements, and then I have some dots in here. Those are elements that are in A and in B. Okay, let me give you an actual example with some numbers now. Let's say B is a set that contains the elements 1, 2, 3, 4, and 5. And A is a set that contains the elements 1, 3, and 5. Okay, so in this example, A is a subset of B because everything that is in A is also in B. Okay, the elements that are inside of A are also in B, right? 1 is in A and it's also in B, right? 3 is in A and it's also in B. 5 is in A, it's also in B. So A is a subset of B. Okay, let's see another example. Let's say I write A equals 1, 2, 3. B equals 1, 2, 4, 8, 16. Okay. Here, A is not a subset of B. Okay. Nor is B a subset of A. So A is not a subset of B. B is not a subset of A. In the previous example, A was a subset of B, but B is not a subset of A, right? Why? Because there are elements in A that are not in B, and there are elements in B that are not in A. Okay. All right. For example, 3. 3 is in A, but not in B. Right?
Professor,
Yes.
for the symbol that you're using, is that like a less than or equal to sign, or is that just a C with an underline?
Yes, it looks similar to the less than or equal to sign, but it's not. It's more like a C. Okay, it's curved.
Okay, thank you.
Okay. All right. Right. So again, less than or equal to will have the point. That would be less than or equal to. Subset will be curved, so it looks more like a C. Okay. Oh, go up to where? To the definition? Oh, okay, sure. Okay. Okay, yeah, I see. A couple people had that question. Yeah. Okay, about the symbol. Okay, thank you for pointing that out. Okay. All right. another example here. Let's say I give you a set A that equals the following. A has the elements 1, 2, 3. B has the elements 2, 1, 3. Is A a subset of B in this example? Okay, so we get some conflicting responses. Some yes, some no. Some people say they're equal. Okay. So what was the definition? Let's go back to the definition. Oop, I'm just going to scroll for a moment. A is a subset of B if and only if every element of A is also an element of B. That's the definition. Let's see if that fits here. Is every element in A also an element of B? Right, those people that said no, it's not a subset before, right? Right, if you look at it now, if you think of it using the definition, keeping the definition in mind, yes, every element in A is also in B. So A is a subset of B, okay? So A is a subset of B, all right? Is B a subset of A? Yeah, right, because everything in B is also in A. Okay, so this sort of gives us now another definition for equality. A couple of you have pointed out that two sets are equal. Well, you're right, they are equal. Okay, so how do we know two sets are equal? Another definition: if the subsets are subsets of each other, then they're equal. Okay, so if A is a subset of B and B is a subset of A, then the two sets are equal. Okay, so in this example, they're subsets of each other, and they are equal to each other.
Professor?
Yes.
Are two empty sets subsets of each other?
Yes. Well, the empty set is a subset. We'll see. I'm going to get to that in a moment. But the empty set is a subset of every set, right? Including itself. Okay. All right. So there's also, since we're discussing this, there's two different symbols that we use when talking about subsets. Okay, there's this symbol, the curved one here with the underline. Excuse me. This means that something is a subset, as we said already. Okay, and then there's this symbol. It's this curved part without the underline. This means that something is what we call a proper subset. Okay. All right, so if it has the underline, it's a subset. That means that it can also be equal, right? It sort of means like similar to less than or equal that we were talking about before. The underline allows for equality. So when I have this symbol here that I circle, that means subset or equal. So subset or equal. Okay. If I don't put the underline, that's called a proper subset. It means it's a subset and they are not equal. Okay, subproper subset. The sets are not equal. One set is smaller than the other. Okay, so if I want to talk about something being a proper subset, I don't want to talk about equality. I will not write the underline there. Okay. Oh, thank you. Okay. So if I go back to this example here that I have right above here, A is a subset of B. A is not a proper subset of B because they're equal. All right, and B is not a proper subset of A because they are equal. So A is a subset of B, but it's not a proper subset of B. Okay. All right. I'm going to scroll back up again for a moment here. All right. If I scroll back to this example here, A is a subset of B. I can write it that way, and I can also write that A is a proper subset of B, like that. Okay. So in the first example here that we did before, both of these statements are true. A is a subset of B. It's also a proper subset of B. Okay.
Is there like such a thing if it's just a proper subset and then another subset?
Say that again. I'm sorry.
Can it be that there's just a proper subset?
Oh yeah, yeah. Well, if it's a proper subset, then it's also a subset. Okay. But if it's just a subset, it may not be a proper subset. Okay. 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 All right. So we now move on to a theorem. A theorem about subsets. Okay. So the theorem is as follows. For every set S, the following two things are true. Number one, the empty set is a subset of S. Okay. So the empty set is a subset of everything. Okay. It doesn't matter what the set S is. And two, S is a subset of itself. Okay. All right, so let's say I ask you to list all of the subsets of the set A comma B. Okay, what are all the subsets of this set with two elements here? All right. So first of all, the empty set is a subset. Okay. Also, the set containing the letter A is a subset. The set containing the letter B, and then the set itself. So altogether, there are 4 subsets of this set. Okay. Yeah. Yep, exactly. Thank you, Afshana. Yeah. Okay. All right, so those would be all the subsets. Okay. All right, so we mentioned before also, I briefly mentioned the size of a set. Let's discuss that now. So let's give the definition for that. Okay. So let S be a set. Okay. If there are exactly n elements, n distinct elements, if there are exactly n distinct elements, in our set S, where n is a non-negative integer, we say that S is a finite set, and that n is the cardinality of S. Okay, so the cardinality of a set S is just the number of distinct elements it has. All right, so the cardinality of a set is basically just its size. That's what we call its size. Okay, so cardinality, I'll write it in parentheses here. Cardinality of a set is its size. Okay. If we want cardinality, we use the absolute value symbol, right? So cardinality of S is denoted by the absolute value of S, like that. So that's not absolute value. It's the same symbol as absolute value, but it's not absolute value. That's referring to the size of the set, the cardinality of the set. Okay, how many distinct elements are in the set S? Okay. All right. So, for example, let's say I have a set S, and the elements are 1, 2, 3, and then a set including the numbers 2 and 3. Okay. What is the cardinality of S in this problem? What is its size? How many distinct elements are in here? 1, 2, 3, 4. Right? There are 4 distinct elements, so the cardinality of this set would be 4. Let's say that's our first example. Next example. Let's say I have a set A whose elements are A, B, C. So the cardinality of A would be 3 in this example. Let's say I have a set B whose elements are A, B, 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 C. Okay. The cardinality of B in this example would be 3. Why 3? Again, because we only count the distinct elements, right? In the definition, we said we look only at distinct elements. Okay. Okay. Somebody had a question from before. Is BA also a subset, or would that just be the same as AB? So BA and AB from before are the same set. Okay, and why again? Because order doesn't matter. Okay. So let me just scroll back for just a moment. Ooh, sorry. Going back to this example here. Okay. AB is the same thing as BA. Okay. So that's considered the same set. All right. These are the same set. Okay, so that's just one subset. Okay, again, because order doesn't matter. Okay. Okay. Any other questions? All right. Let's also discuss what a power set is. Okay, so let me give you the definition for a power set of a set S. Okay, so definition. Given a set S, the power set of S is the set of all subsets of S. Okay. The power set of S is denoted by P of S. Okay, so P of S is a set. It means the power set of S. Okay. So that is the set of all subsets of S. So anytime, if something, for example, let's say we want to talk about all the subsets of a certain set, that would be its power set. Okay, so if S is the set A comma B from before, the power set of S is the set of all of its subsets. We listed those before. So the power set of S, P of S, would be the set including the elements. The empty set, the set with A, the set with B, the set A comma B, right? That's the set itself. Okay, so this would be the power set of S. Okay. All right, anytime a set S has cardinality n, its power set will have a cardinality of 2 to the power of n. Okay, so if the cardinality of S is n, the cardinality of P of S is 2 to the n. Okay, so in this example, in this particular example, the cardinality of S is 2. So the cardinality of its power set would be 2 squared, which is 4, right? And there are 4 elements in the power set. Okay, so that's in general how you would know how many elements are in a power set. Okay, any questions on that? Okay, if there's no other questions, we'll stop here for today. We'll finish up 2.1 next time and move on to 2.2. Okay. I'm going to give you guys some homework also to do on what we've done so far. And I will see everybody next week. Again, I believe we don't have class Monday. So I think we'll see everybody on Wednesday. Okay, you can double check the school calendar to be sure, but I'm pretty sure we don't have class Monday. All right, everyone, let's do attendance. And then I will say goodbye, and I'll see everybody next week. Okay. All right. Yes, sure.
I have a question about the proper sets. I was a little confused. Would you be able to quickly go over that?
Oh yeah, sure. Yeah. If basically, if a subset has less elements than the bigger set, then that would be a proper subset. Okay, so for example, this is a proper subset of this because it's got less elements. Okay, so I could write it this way. I'm allowed to use this symbol here. I'm also allowed to write it this way. Both of these are correct because this means subset. Proper subset means subset. This means subset or equal. Or equal. Okay, so it's subset or equal. So I can write it this way as well. As long as it's one of the two.
Okay.
All right. If you still have some confusion about it, you can ask me again next class. I'll go over it again.
All right. Thanks.
No problem. Okay. Any other questions? All right. I'm going to head out. I'll see everybody next time. Take care.